My name is Florian Kluger, and today I will present you Cuboids Revisited, learning robust 3D shape fitting to single RGB images. The goal of 3D shape abstraction is to represent an object with relatively few volumetric primitives, such as cuboids or superquadrics. Previous works predict primitive parameters directly using artificial neural networks and provide good results for single isolated objects. When applied to more complex real-world scenes, however, these methods either fail completely or do not provide reasonable abstractions. We now present a novel approach for this problem, which does. It is based on the concept framework and reformulates the problem as a robust multimodal fitting task. It is end-to-end trainable and does not require any manually annotated ground truth labels. We begin by extracting 3D features, such as a depth map, from the image using a CNN. With a second CNN, we predict sample weights for each feature. We then sample minimal sets of features, fit cuboids to them, and select the cuboid with the most inliers. Lastly, we take the inlier map as a state tensor, feed it back into the sampling weight CNN, and reiterate. Step by step, we recover cuboids for all structures in the scene. One key aspect of our approach concerns the handling of occlusions. Take this little example of two cuboids, A and B, a set of points describing the scene, and a camera which is observing it. The average distance of all points to each cuboid is the same. One side of cuboid B, however, occludes all the points while not representing any structure in the scene. Cuboid A, on the other hand, does not occlude the scene at all and is therefore a much better fit. In order to resolve this ambiguity, we devised an occlusion-aware distance metric. As one would normally do, we measure the minimal distance to any cuboid surface if a point is not occluded. If it is occluded, we measure the distance to the most distant occluding surface instead. In addition, we devised an occlusion-aware inlier counting function which explicitly penalizes occlusions. As can be seen with this example, our occlusion-aware inlier counting results in much more sensible abstractions. During the sampling and fitting stage, we first select a minimal set of feature points using the predicted sample weights. With these feature points, we estimate initial cuboid parameters using a simple heuristic. We then minimize an objective function which measures the distance between the feature points and the cuboid surface using an iterative optimization technique such as LBFGS or ADAM. We repeat this process multiple times independently in order to produce a set of cuboid hypotheses. With our occlusion-aware inlier counting, we then select the best cuboid hypothesis. We append this cuboid to our set of already selected cuboids, and our pipeline continues with the next iteration. In order to facilitate end-to-end training, we derived the gradient for the cuboid solver analytically using the implicit function theorem. We evaluate on the NYU depth v2 dataset and measure the distances between the predicted volumetric primitives and the ground truth depth. We measure the regular Euclidean distance as well as our proposed occlusion-aware distance metric. We report the averages of these distances as well as the area under the recoil curve for various upper bounds of the occlusion-aware distance. In addition to RGB images, we also consider using the ground truth depth directly as the input. We compare against variants of a state-of-the-art competitor, which represents the scenes using superquadrics, and also against a sequential Rensec baseline, which uses cuboids. As you can see, our method outperforms them by large margins with respect to all metrics. This improvement is not only measurable, but also clearly visible in these visualizations. In comparison to the superquadrics-based competitor, our abstractions are much more sensible and are able to represent the general arrangement of the most prominent objects in the scene. Thank you very much for watching. Code and pre-trained models are available on GitHub.